Welcome back. This is the last experiment of this very innovative program that has been decided to be created by SCST RTI to reach out to students of remote areas. The last experiment that we are going to discuss today is to draw the IV characteristics of a PN junction diode in forward bias and reverse bias. And for this we require a simple PN junction forward bias reverse bias apparatus, which is usually ready-made, so all the connections are usually made. But if there is no such apparatus, you can design the circuit very easily. I will be showing you how to create the circuit in a very simple way. You just need the PN junction diode, voltmeter, ammeter, a rheostat, a power source in the form of battery alternator, a one-way key, and of course some connecting wires. Now, what exactly is a PN junction diode? Well, PN junction diode is a one-way device. So we all know about P-type semiconductors and N-type semiconductors. If you have silicon or germanium and you dope it with pentavalent impurity, then you get N-type semiconductors. For example, if you add silicon with phosphorus with silicon, then you get an N-type semiconductor where the majority charge carriers are electrons. Similarly, if you take silicon and you dope it with trivalent impurity like aluminum, then you get P-type semiconductors where holes are the majority charge carriers and electrons are the minority charge carriers. So individually N-type and P-type usually they don't have much of use. But when you form a metallurgical junction of N-type and P-type, that is when you get the PN junction. And there is a process of how PN junction happens. You might have already studied about diffusion process, then the formation of the depletion region, and then the drift process, and finally when diffusion and drift current equal each other, then the PN junction is stabilized. So if you look at a PN junction, so if this is the N type and this is the P type, the N side has donor atoms, usually the phosphorus atoms, and on the P side we have aluminum atoms, which are the acceptor ions. And this is the depletion zone. So if you plot the potential graph, then potential remains constant. Only there is a drop in potential across the depletion layer. So this is your depletion layer. And this potential difference is sometimes called the barrier potential. So this is what is called an unbiased PN junction. So there is no transfer of electrons from N side to P side, or there is no transfer of holes from P side to N side, or there is no transfer of charge carriers across the PN junction. So the PN junction is now stabilized. And there is a depletion zone that has been created, and there is a potential difference between N side and P side. N side is at a higher potential than P side because N side has lost negative charges and P side has gained negative charges. So, if I want to determine this barrier potential, one of the ways is to forward bias it. But now what exactly do you mean by a forward bias? So there is no way electrons or holes are getting transferred across the PN junction. But if I want to do that, if I want to ensure some electrons flow, so I have to give some support or help from outside. That is where I bias the PN junction, or I support the PN junction from one end or the other so as to ensure that there is a flow of charge carriers. So first we will study about forward bias. But before we proceed, the circuit symbol for PN junction is this. The triangle represents P side and the bar represents N side. So what is forward bias? A very simple explanation. So if P side is at higher potential than N side. Then we call that as forward bias. Similarly, if the N side is at a higher potential compared to P side, then it is called reverse bias. So if other way around, if N side at higher potential than P side, it is called reverse bias. And we will study something, we will try to study the variation of current when with the applied voltage, and that graph is called your diode characteristic. So first thing that we will study is how to forward bias and study the forward characteristics of a PN junction diode. And similarly, we will go over to reverse bias. So let us quickly see what is the basic circuit diagram for forward biasing of a PN junction. So if you take the PN junction, I am drawing a very simplistic diagram. You can draw this diagram or the one that is mentioned over here in the board. Both of them are the same diagram. These are the simple. I am just drawing a simplistic diagram. So you can see I have a milliammeter to measure the current, to track the current that is flowing. I have the voltmeter to find out how much is the potential drop across the PN junction. I have a source, a variable source. You can associate a rheostat with it, a battery limiter and rheostat. I have just combined it to look it like one variable source where you can adjust the applied potential and simply execute. So what is the purpose here? How are we going to study the diode characteristics? Well, the idea is very simple. What I will do is, I will start increasing this external potential. Okay, I will start increasing this external potential. See, already there is a barrier potential directed from P side to N side. There is an electric field which is directed from P side to N side. So there is a barrier potential. So, the other way around. N is at a higher potential, P is at a lower potential. So now I apply an external potential. So slowly I go on increasing the applied potential, the external potential, and I observe that how much current is flowing through the diode. That's it. That is the experiment. I go on increasing the applied potential. I observe how much actual potential is being applied, and I observe the variation in the current. And you should expect a graph like this. The current will be in milliamperes, applied voltage will be in volts, and you should expect a graph like this. That means initially there will be no current, but then after some time there will be some current, and then the current shoots up. Remember, the P side is now connected to positive terminal, N side is connected to negative terminal. So that is what it means that we are doing what? Forward bias. And then if I want to study what is reverse bias, all I have to do is interchange the polarity of the applied cell, of the battery. Only thing to note here that in reverse bias, P side is connected to the negative terminal and N side is connected to the positive terminal. And here the applied potential and the barrier potential are in the same direction. So the direction of the current is also reversed, as well as the sense of the potential application is also reversed. So since the direction of the current and voltage are opposite to what we have in forward bias, we are going to plot the graph in the third quadrant. And one thing to note that in forward bias you are going to see large number of electrons going from N side to P side. So the current will be large, and that is why we have a milliammeter. But in reverse bias there will be very few electrons on the P side which will be coming to N side, the minority charge carriers. So therefore the current will be much less. So I have a microammeter connected. Remember, forward bias involves movement of majority charge carriers. Reverse bias involves movement of minority charge carriers. That is why meter, milliammeter, and here we have a microammeter. And then if you plot the graph, that will be in the third quadrant. And of course the intervals will be different. Here in reverse bias you can increase the voltage by large intervals, but in forward bias the voltage will be increased at small intervals. Very small, maybe 0.2, 0.4, depending on the nature of the semiconductor diode. But here you can increase it 2 volt, 4 volt, 6 volt, 10 volt. Just mind that the current here is in microampere, voltage is large. So you will see that the variation is like this. So this is the reverse characteristic, this is the forward characteristic, and if you combine both the graphs, then that is called the diode characteristics. And ma'am will now explain how we can obtain the diode characteristics. That's it from my side. Thank you so much.
We reached at the final stage of this workshop. Now, this is your last experiment to plot IV characteristic for PM function in case of forward biasing and reverse biasing. Everything is very neatly explained by sir. Now, we have the setup built in, everything is built in inside. All connections are done. Only you have to adjust or arrange for forward biasing and reverse biasing. Okay. Here, as it is mentioned here, there are two connections, one for forward biasing, the other one for reverse biasing. When you will do connection for forward biasing, you will bring the toggle key upward. Then, whatever it is written here, that is the range of the milliammeter and voltmeter for forward biasing. Here 10 milliampere is the range of the milliammeter. So 10 milliampere is taken in the lower scale, 10 milliampere. So for forward biasing you will use the lower scale. And 2.5 volt is here in the voltmeter in the upper scale. So you will use this for forward biasing. The upper scale to be used for the voltmeter for forward biasing, and this milliammeter, that is the lower scale of range 10 milliampere to be used for forward biasing. First of all, you will note down range, least count and zero error of voltmeter and millimeter. As the range of the voltmeter is 2.5 volt, for forward biasing range of the voltmeter is 2.5 volt, least count, for least count 0.5 volt is divided to 10 divisions. So least count is 0.05 volt and zero error is 0. Similarly, for milliammeter, range of the milliammeter is 10 milliampere and 2 milliampere is divided to 10 subdivisions. So least count is 0.2 milliampere and zero error is 0. So we have set it for forward biasing. Now for connection, only P side will be connected to, P will be connected to positive and N will be connected to negative. N will be connected to negative. Done. So P is connected to positive, N is connected to negative. So forward biasing connection done. Only switch on, bring the regulator to the beginning, switch on, we will make a column for forward voltage and current. Forward voltage, current, and regulate this. Initial reading, when V is 0, I 0, then regulate it so that the pointer comes to, suppose it comes to second division. Pointer is in the second division. So voltmeter reading is 2 into least count, that is least count is 0.05, 2 into 0.05, that means 0.1 volt. Here the pointer is on the first division, and as the least count is 0.2 milliampere, so here reading is 0.2 milliampere to be noted. Then change it a little. Pointer comes to fifth division, so 5 into least count, that is 5 into 0.05 is the reading of the voltmeter. Now the pointer comes to the second division, so 2 into 0.2, that is the 0.4 milliampere is the reading. See, go on changing the regulator only. Note down the division on which the pointer lies multiplied by the least count will give you voltmeter reading. Similarly, the division on which the pointer lies multiplied by the least count will give you the milliammeter reading. Go on regulating and take down, note down 12 to 15 readings, then plot the graph. You will get almost similar graph, and that will be the fast forward. Next, switcher. We will start reverse biasing. Connection for reverse bias. See, only to be reversed here. Here you find the reverse biasing rating. Bring the topic downward. This is the range of the voltmeter and the micrometer for reverse biasing. 50 volt. Range of the voltmeter is 50 volt. So you will use the lower scale. 10 volt is divided to 10 divisions. So least count is 1 volt. So for reverse biasing, least count 1 volt, range 50 volt, 0 error, 0. Here also, range of the microammeter is 100 microampere. That means 20 microampere. According to that scale, 20 microampere is divided to 10 divisions. So least count is 2 microampere. 0 error, 0. Then connected for reverse biasing, P is connected to negative side, N is connected to positive. So reverse biasing done. Switch on. Bring the regulator to the beginning. Note down the reading of voltmeter and micrometer. Initially V0, I0, then slowly change. Suppose the pointer lies here on the third division. 3 into least count, that is 1 volt. Voltmeter reading 3 volt. And here, in case of micrometer, the pointer lies on fifth division. 5 into least count, that is 2 microampere. So 10 microampere is the observation. So go on rotating. Note down the number of divisions multiplied by the least count is voltmeter reading. Number of divisions multiplied by the least count is the micrometer reading. Similarly, note down 10 to 15 divisions and plot the characteristic curve. And we will get similar graph as it is not there. Reverse bias. I hope we have completed our experiments, and we expect a feedback. All of you can suggest if you want, and you can refer to any other practical books, maybe Lakshmi publication, comprehensive, or GRB, any other publication for reference.